Hello, my name is Kavi Legate, and this is Lab 3, the black hole. So for the purpose of this, it is to find the mass of a black hole according to the motion and orbit of a star, utilizing the idea that the only net force acting on a star is a black hole, and by using this calculated mass, we will then find the initial velocity of a spaceship so that it flies around the black hole without crashing. As a preview results, we're first finding the mass of the black hole, and we're using that to calculate the initial velocity specified above. For fundamental physics principles, since the only force acting on the star is the force of the star by the black hole, we can then assume that F net is equal to the force of gravity of the black hole. The only force on the spaceship is the gravity from the black hole and the gravity from the planet. So in this case, F net is the force of gravity of the black hole and the force of gravity of the planet. And if F net parallel is the same direction, the magnitude increases and the magnitude of motion increases. And if the perpendicular component changes, the direction of the star or spaceship changes as well. For formulas, we have Newton's second law, which specifies that the net force is equal to the parallel and perpendicular components. We can further break that down by saying the parallel component is the change in momentum over delta t times p hat, and the perpendicular component is mass times velocity squared divided by the radius of the kissing circle times n hat. We also use the universal gravitation formula specified here, and since we're assuming that force of gravity is equal to net force, we can then find the mass, which is equal to the magnitude of the change of momentum times the radius squared divided by the gravity constant times the mass of the planet. So this is what we'll be using in the code to find the mass of the black hole. So for the initial conditions, the system is a black hole, surrounding is a star, and the mass of the star is what's specified in the problem. The time increment we saw is 1 day, which translates to 86,400 seconds, and we're using the gravity constant as well. In the code, we have the gravity constant, the star mass, and the delta t that we saw before. And in this, we're using initial and final to calculate the final and initial momentum by multiplying it by mass, and then we're using this to calculate the F net, which is equal to the change in momentum over change in time. We are then calculating the parallel component and the perpendicular component right here, and we're using that to calculate the mass of the black hole, which was specified before right here. So for results of finding the mass of the black hole, we found that it was 1.43 times 10 to the 34th kilograms, which is what we'll be using in the next section, along with the magnitude of F net parallel, and F net perpendicular as well. So the initial conditions for the second part is the system being the spaceship and the surroundings being the black hole and planet. Additionally, we have these three, the mass of the black hole, planet, and ship, which we'll be using in the code right here for the initial conditions. To find the initial velocity, we'll be using the guess and check method in order to put in different values to see when it doesn't crash. Here we're calculating the net forces. So for the net force on planet, we're utilizing the net force of the black hole on planet plus the net force of the ship on the planet that we calculated here. Additionally, to find the net force on the ship, we're using the net force on the planet on the ship. Additionally, we're also using the net force of black hole on the ship. And we're using these two values to find the planet velocity with the planet position with the position update formula, and doing the same with the velocity update and position update formula in order to calculate the final velocity, the initial velocity. So for our results, the guess and check method led me to find that -6 times 10 to the 6th and -7 times 10 to the 7 meters per second will be the initial velocity that allows the spaceship to not crash while doing a full revolution. So for discussion, the average mass could have been calculated with more data points and a longer time in order to be more accurate for part 1. For part 2, velocity could be found larger than the more accurate initial velocity, and since I used the guess and check method, and a longer time interval could have been used to get a more accurate calculation for velocity. And for further questions, for the what does it mean, the rate of change in momentum is delta p is equal to F net delta t. So the net force is equal to change in momentum, which also means that F net parallel, F net perpendicular are the same as delta p as well. And for the what if, the x component of the initial velocity must be smaller and negative to avoid any collisions. So this is an example of a sample code where we do a -0.6, which is less than 1. Thank you.